When you add a ball onto a metal rod, the rod will stretch due to the ball's weight, pulling it downward. The amount that the rod stretches is governed by a property called Youngs Modulus. And this is a concept that a lot of students have some difficulty visualizing. So I've set up this code to help walk you through the calculation process and be able to test the results of the simulation against an experiment. We start with the inputs. We need the unstretched length of the rod. We're going to call that L0. So that's the initial length of the gold rod over here. We need to set up the radius of the rod because depending on how thick the rod is, it's going to respond differently to the weight of the ball. And then we need the Youngs modulus of the rod. This is a value that you can look up in your textbook or in a table online, but this is usually a very, very high number. So we're going with 10,000 right now, which is actually kind of small for a Youngs modulus value, depending on the units, of course. And then here we're putting in the weight hanging from the rod. So that's the weight of the red ball here at the bottom. So to help us remember where a fixed point is, we're creating a ceiling. That's the gray box up here. That's just there for visualization purposes. And then we hang the rod from the ceiling. So the rod here is the yellow cylinder here in the center of the visualization. It's going to be fixed up at the ceiling here. So its position is up here at the top where the ceiling is located. And then it's going to point downward. That's why its axis is 0, -1, 0. So it's already going to be pointing downward at the beginning. And then here to help with the visualization, I've set the scene auto scale to be false, so the scene will not automatically scale. You can turn this back to true if you need to as you're working with this code. So then we add the ball at the end of the rod, just like you would hang the ball onto the rod in an experiment. And then we have to calculate the change in length of the rod. That's this delta L calculation here. And this is using the Youngs modulus equation. Youngs modulus gives you the ratio of the stress to the strain. The stress is the amount of force that the rod experiences divided by its cross-sectional area. So when you look at this cylinder, if you look at it head on, it's going to make a circle. And so we need the area for the circle is going to be pi times its radius squared. And so when we take the weight and divide it by that area, we're getting the amount of stress that the rod is experiencing from the ball pulling it downward due to its weight. The strain, on the other hand, is the ratio of the change in length of the rod to the rod's original length. So it's the fractional change in length. So Young's modulus is the stress over the strain. You rearrange that equation and you get out this equation for delta L that allows you to calculate the change in length of the rod. So there's a lot of variables in here that we'll be able to test in just a minute. But then we adjust the rod's size so that it increases by delta L. So in other words, the length along its axis is going to increase by this amount delta L. And then, of course, we need to move the ball down to complete the animation. Now, to help us visualize this process, I put in a couple of sleep functions. So this is going to tell the code to hold for just 2 seconds while we visualize the rod by itself. This will cause the code to hold for 1 second while we visualize the ball being added to the rod. That's why when you run this, it goes in a few discrete steps. So there it sleeps for 2 seconds. There it sleeps for 1 second, and then we have the stretch. You could change those values if that's too fast or too slow for your liking. You can change those to any value of seconds that you would like. And so obviously there's a lot of inputs that we can play around with here. For example, if we make the ball heavier, we would naturally expect the rod to stretch longer. So right now we're getting a strain of 0.06. So the length of the rod is changing by just over 6%. Let's try doubling the weight of the ball that's hanging from the rod. And you can see we get a longer stretch. And in fact, it's twice as much. It's 12% and some change. That makes sense. We doubled the weight. We should double the amount it stretches by. We can also make the material stronger. Let's suppose I trade out my metal rod here for something stronger. Let's increase its Youngs modulus by a factor of 3. So with a stronger Youngs modulus, it's not going to give as much. There isn't going to be as much stretch. We're down to 4% strain now. We can also make the wire longer because according to this, if I have a longer initial wire, I should have a longer stretch. So let's increase the initial length, let's say to 10. So we'll more than triple the length of the original rod. We add our weight onto it and look, it stretches. It has a longer stretch visually, but you notice that the strain is the same. It's still 4% because the strain, you might remember, is the change in length over the original length. And so the strain is going to be the same, but the actual amount it stretches by is going to increase. So I hope that visualization is helpful for you as you work with Young's modulus and stress and strain. Do try out the problems at the end of the video to further explore this topic.